I would like to thank Scott for this invitation and for organizing this wonderful conference. Happy to share this work and hoping to get some feedback. It started as a class project with one of our PhD students. We set out to understand the statistical XG in a slightly kind of different but more insightful way. So what I will do, I will talk a little bit about the statistical challenges here. Since yesterday we have had some wonderful talks, and soccer is not necessarily an easy game to analyze or kind of model, and so there are complexities here, and so some of them will come. I'll particularly touch on some of the modeling aspects and some of the technical side here, and what we'll see is a form of simplifications, and that will provide some intuition and insight about maybe how we can understand expected goals, and we'll kind of talk a little bit about stochastic modeling of sorts and goals. We'll talk a little bit about itemized response theory, how that plays some role here, and I'll also show you some EPL data analysis. Now, the statistical literature on soccer analysis is, it goes a long way, and some of the early work focused on kind of event modeling, Poisson models for soccer goals, and also Markov models for event transitions, some of which our team mentioned. And so the same framework I'm going to use here in an interesting way, even though main focus is on XG. And obviously in recent years, or maybe in last 2 decades, the expected goal has taken over the field, and maybe more machine learning kind of modeling than statistical modeling. So we'll still be interested in kind of the statistical aspect of it, and kind of more interpretability, more insight. Back in 2004, when I was looking into some of the early work, some of the early XG models were just logistic regression models with contextual variables, and they identified some of the key contextual variables, like maybe distance and angles, and whether or not there is a defender within a meter or two of the shooter, and whether there was anyone between the goalkeeper and the shooter, things like that. So obviously, these kind of models, they are maybe a bit simplistic, but they are very interpretable. They provide insight. Versus more machine learning models where we can throw in almost any information. It can include interactions, add more complexities, have better prediction power, but then there is that trade-off between the interpretability and the prediction accuracies. And so, ideally, what we would like to do, we'd like to have a bit more intuition about the expected goals. Even though it's a number, we want to understand how these expected goals can be decomposed to understand relative contributions of different factors. And that could be, again, maybe the spatial location of the field, from which the shot is taken, or other contextual, again, characteristics, which could include many things, maybe the defensive formation, or whether the shot is taken with right foot versus left foot, and things like that. Okay, so that's the idea. Now I am coming from a background on on spatial statistics. So the soccer field has some interesting symmetries. Obviously, one symmetry is that is divided into two halves, attacking half and the defensive half. But there is this other symmetry, which is the horizontal line here. It divides the field into two halves based on the right foot and the left foot, meaning that if a player is taking a shot from these locations to the goal with right foot, that's essentially very symmetric in the sense there would be a point here, kind of the mirror reflection point right here, where a player can take a shot with the left foot and it will have similar effect. Now we want to impose this kind of symmetry in the analysis, particularly in XG, and is very kind of important, very much like for the way Tim was using some symmetry informations in the Markov chain transition probabilities. So here what I'm plotting are real data, EPL soccer shot data for last 10 years. So that's the kind of largest amount of data I could gather from world football, or going up to like maybe 10 years of data. And so all the gray dots are kind of locations from which a shot is taken. And now we are actually just looking only one half of the of the field. There are few shots that were taken more than halfway of the pitch. We excluded them from the analysis. So these two pictures are for open play, whereas the bottom one are for the set piece. And if you see a black dot, those are the shots that actually ended in a score. And you will see some reflections of that symmetry. These are for left foot shots, and these are for right foot shots. For example, some of the score were happened essentially from the corner position. And that is completely missing here. So you will see there is a bit of asymmetry as far as right foot or left foot is concerned, but there is that reflectional symmetry. So that's a little bit present in the data, and we are going to impose these as well. So that's one interesting aspect of the analysis. The other thing is we are going to use kind of a Markov property of the like how the game is played. So we will treat soccer as a dynamical system, some kind of Markov process where the game starts maybe from maybe a goal kick or a kind of a maybe kickoff, some kind of starting state, and kind of it moves from one state to another. Maybe different actions happen. Maybe it's kind of passing, dribbling, all kinds of things happening, and then once in a while maybe there would be a pausing state, and typically they could be a goal kick, they could be a again kickoff and things like that. And even though the game starts here, it goes in kind of many phases. When we are interested in probability of scoring a goal from a shot, so we are focusing on the very final action, and this final action would typically be a shot at goal, right? So that's a very kind of interesting event, and because there is almost like a pause after that most of the time, and then kind of the game will kind of start again. There are some situations where it may not happen. Maybe there is a rebound, right? And so some of these rebound and etc. we are going to discard from the analysis. Now, this part is very important because in Markov chain theories, there is a notion called excursions. Like the Markov chain, it starts from some kind of starting state, it moves around, and then it goes back to that kind of the pausing state. And these excursions are essentially interesting in the sense that the Markov chain kind of repeats again and kind of try to do the same thing. But obviously there are a lot of stochasticities involved, so we see different excursions every time we see the game. So the game has some of these repetitions, but mainly because of these excursions. And what we are kind of looking at is essentially most of the time the last actions in the excursions, and those are typically short at the goal. Okay, so we are not going to assume these excursions as kind of independent kind of event, but we are going to assume that they are some kind of exchangeable event. So kind of conditionally independence rather than actual independence. Okay, yes. Now I'm going to kind of move forward. The whole idea is, if we want to understand this kind of expected goals, two things are important. One is the short, the last action, as well as the outcome of the short, like the position of the short that last action has happened, and the outcome. So, but that's actually a difficult problem. But what happens is, under some kind of conditions, certain simplifications are possible, and this simplification is very key to kind of have a kind of a more interpretable and insightful understanding of shockers, particularly expected goal calculation. So ideally, what we want to do, we have the spatial locations, time, we have different contextual variables, maybe they are all coming from the tracking data, all kinds of contextual variables we can think about. We have two things. One is whether a shot is taken from that location from that time, and then the outcome of the shot. And in this context, we also have different latent or some kind of factors or kind of persistent components, and these are kind of player skills and team skills and things like that. And so typically we would have different sets of these latent factors or persistent unobserved components. Some of the skills might be needed to generate the shot or the create opportunities, but then when it comes to scoring, like what matters is the conversion skills, and the conversion skills are typically different. They could be the skills of the striker, they could be the skills of the goalkeeper to prevent the ball, shot, or they could be the skills of the defender to block the shot, etc. And these two different skills, are kind of key to simplify the problem. There may not be a lot of overlaps. What generates shots versus what helps convert the shots into goal. And if we have that, then what happens is, if we are asking what's the probability of scoring a goal, what's the outcome, given everything else and the math history, it does depend on the contextual variables. It does depend on a subset of these kind of persistent factors and some parameters, and maybe this G is something what we call kind of link functions. So there is a simplifications of this conditional probability. And similarly, for the other part, where we have the way the team is scoring, kind of creating opportunities, that depends on other sets of skills, and that does not depend on those parameters involving this conditional variable. So what happens is, because of this, we have a simplifications of what we call the likelihood functions, and primarily for xg we are interested in making inference about all these parameters and those particular skills that allows us to a team to convert goals. We can put priors on them, and the posterior distribution simplifies. They becomes actually a form of hierarchical binary regression. So that simplification is awesome, because what it means is that we can use contextual kind of variable, do binary regressions, and kind of do the regression analysis. So what this means that we can take the outcome of the shot, and we can put all the explanatory, all the contextual variable we can think of, and kind of set up a complicated regression model. Now, this process is, the other interesting is very similar to what it seems like itemized response theory. Originally, it started in psychology or in educational testing. Like you throw students different questions, questions of maybe different difficulties, and based on their skills, they answers, and answers can be correct or incorrect. And similarly, when a player is taking a shot from different locations of the field, the location itself, the distance, angle, creates certain intrinsic difficulties, and then there are other contextual variables and the skills. So it's essentially the items here are the scoring opportunities. They are generated stochastically, and then we see the outcomes. And it's more like a group response than an individual response. So it's kind of a bit more general versions of multidimensional item response theory. And then we have this spatial symmetry, etc. So we want to put all these here and fit a very large binary regressions model. Now I'm going to skip a couple of these technical side, but the idea is you want to throw in almost anything: players effect, location effects, the game advantage or the score line, the time, the attacking team effects. Maybe they do drills together, and so they have some strategies in place. They also may do defensive drills together. They also may have defensive strategies in place. Maybe the defensive formats, things like that. And then also the spatial effect. A little bit about the spatial effect. We are going to do a little bit of discretizations. We are going to divide the field into kind of 1-year squares. Time maybe into some intervals, and then the thing about this so in this model I have thousands of parameters. So about 1,500 players they took shots. So every player will have an individual player's effect. For every locations, every square cells, I have a kind of a spatial information that's like the intrinsic difficulty of scoring from that kind of location of the field, etc. And so there are ways to put priors on them. So one way to do that is that maybe I want to understand kind of how difficult it is to score from a location here. Maybe it's average of the 4 nearest neighbor, and kind of and there are some uncertainties, more like Gaussian uncertainties. And so all the priors I'm going to put are like non-informative priors, so I'm not going to assume much. Is going to give us a kind of a very complex model. So this is kind of the spatial prior is kind of all over the place. We are not going to see much or expect much pattern, but it's just kind of out there. And then eventually what would happen is it's just a very kind of complex binary regressions, right? So and we need to do Markov chain Monte Carlo simulations to get to the answer. So what we did, we ran it to this EPL data. We have like 10 seasons, about 380 matches. Obviously not all team plays in all seasons. On average, about 26 goals taken per match. So I have about 75,000 shots, many thousands unknown. So you would not be able to run it, with any R package easily, but we discounted, these rebounds and etc. because rebounds can change the contextual variable. Also, the persistent skills also change slightly. So we want to kind of stay kind of together. I'm going to show some of the analysis. So for example, for individual teams, like Manchester City coming on top, Leicester, Tottenham, etc. And then some of the defensive teams are here. This is like a 2D plot. Ideally, you want to look into kind of on this side and on this side. The hierarchical cluster kind of doesn't make a lot of sense here. Then, all these different contextual variables, maybe I'll highlight a couple of them. I'll take maybe 1 more minute. So one thing what we noticed is that for short conversions, home effect is slightly negative, meaning that if you are playing in a home ground, there is a less chance of scoring. Okay, this is very opposite than what the way we understand home effect. So home team wins more games, but that's because they create a lot more opportunities to score than the away team. But their conversion rate is a little low because they take more risk. So these are like, if, winning teams play more confidently. So if the score line is in your favor, you convert better. the middle of the game in both halves, the conversion rate increases. For different seasons, the score conversions went up a little. It's kind of pretty stable. Some defensive formation, gives you an edge. Maybe it helps you block shots better. There is a little bit of effect of right foot, has a slightly better probability of scoring. And open play versus set piece has lower probability of conversion. So maybe that's the reason, the team scores, they commit fouls. Maybe that's the way to save. So I, obviously, I just kind of, I don't have a lot of time. So what I will do, so these are some of the spatial plots. And so what you are seeing is a picture for the right foot, but maybe I have a better picture here. So if someone is taking a shot from the right foot, these are the different level plots. So on this side, you have higher probability of scoring. For left foot, from this side, you have higher probability of. But there are also areas where, the chance of scoring become a bit less. So that's what kind of the data is showing. So sometimes, it's easy to probably score a bit from a longer distance. So the angle and the distance, there are a bit of interactions. That's what we found. I think I'm going to stop here because I'm running out of time. Better to hear some questions and get some feedback. But I mean, one thing leads to another. I'm interested in how yellow cards and red cards, changes things. And maybe I'm interested also in kind of machine learning version of XG because, if you can do the statistical version, you can also think about that versions with tracking data, etc. So I'll stop here and see if there are questions.